Right, ready to start the final session of the day. I must admit, when I saw the title of this talk, 50 years of visual photometry, I thought there must be a typo. It can't be anything like that. It's sort of like this.
Very young.
Yeah, very impressive. So John is one of our premier visual observers, as you will know, and we were lamenting over the tea break there about the slow decline in the number of visual observers, except for the last couple of years when we've had that uptick, which is great to see. It's disheartening when I look at some of the perhaps slightly lesser known MIRAs, and you see like curves of the last 4 or 5 years, and there may be 4 or 5 people observing them. So it's thanks to people like you, John, that continue to carry that forward, and I hope others will join you. I always think of John's articles in the variable star section circulars, his travel logs. His travel logs are great fun. He's traveled the world over the last, apparently 50 years. Perhaps we might hear about some, I'm hoping we might hear about some of those, but you will, in terms of his observational challenges from all sorts of unusual parts of the world. So John, over to you.
Thanks, Jeremy. So earlier this year, I think it was 9th of May, I made an observation of Aurora Borealis, which was exactly 50 years to the time and date when I made my first observation of Aurora Borealis. So I thought that today would be, that's a good reason to inflict upon you all an observer profile. Here goes. I'm a visual observer, so I'm going to make this presentation is very visual. It's 59 slides, 30 seconds a slide. I'm going to go real quick, but it's very visual. Lots of pictures, lots of. Okay, anyway, let's get going. Okay, so here we go. We'll go right to the very beginning. This is before I had any knowledge of variable stars. Or my knowledge of variable stars was roughly equal to my knowledge of or awareness of haircuts. So at the age of 12, my parents bought me a 6-centimeter refractor, which was bigger than me, as you can see on that picture. And that's what got me going. So straight away, 1973, astronauts had walked all over the moon. So I thought, right, go straight for planets. So on the left-hand side, what you've got up there, that's my first observation, 9th of April, 1973, planet Saturn and Titan. And that's how it appeared through that telescope. Also observed the other bright planets, Venus, which is not shown on here, Mars at the bottom, also Jupiter. And we've all done this. We've all observed Jupiter and sketched the Jovian moons as they move from night to night. So this is how I got started. But there were only four planets, and I needed something more interesting. So I joined the local astronomical society, which was Salford Astronomical Society. Young bunch of people there, aged between 13 and 25. I think that's the oldest person there. Don't know where those young people are nowadays, but that showed the interest that there was in astronomy in those days. And so within that astronomical society, they had a Messier objects section, deep sky. So I got into deep sky observing. I didn't have enough money to buy any star charts. So what I did, straight after school, went to the local library, which was well equipped with star charts. I traced and drafted lots of star charts so that I could learn the sky and I could find the deep sky objects. These charts, they're at the back. They're all on display if you want to peruse them. But these got me going. We're very quickly, within 1975, I knew the northern sky down to 4th magnitude, and in some areas much deeper where there were interesting objects. These are 2 of the constellation charts. That's Cygnus, that's Draco. On here, I've actually marked on this chart Nova 1975. It was scribbled on afterwards, after this chart had been drawn. So deep sky objects. In 1975, I set out to observe every Messier object. So we've got Messiers 1, 2, and 3, and 93, 94, 95. And they were all sketched exactly as I saw them through the finder scope and the main telescope. Some of those observations, some of those sketches got into the Webb Society handbook. And I find it really interesting. Well, I find it amusing, really, that my telescope was 2¼ inch refractor was listed alongside the Anglo-Australian telescope, the McDonald telescope, and the Mount Wilson telescopes in those days. So I always think that's amusing. So first, variable star observation. Here it is in the database. So I used this pencil chart here to make that observation. I use this comparison star. It's listed as comparison star MAG 66. I estimated our corona borealis to be half a magnitude brighter. It is actually comparison E, which is here, E plus 5, and that's my first observation. If you look at some of the names there, I think there's only maybe Guy still around, perhaps. It's a long time ago. Who else have we got? Fantastic. Well, they need to. Okay. Anyway, having started those observations, when I got to my number 16th observation in 1975, I was looking at Chi Cygni, and what did I find? I found a comet next to it. I'd never seen a comet before, but I'd independently discovered it. So I didn't know what to do with it. I reported it to Salford Astronomical Society. They didn't know what to do. There was no internet in those days. How do we report it? What do you do in the mid-70s if you got an astronomical issue? Well, let's ring Patrick Moore. The director of the observatory looked in directory inquiries, looked for Patrick Moore's number, found it. He actually picked up the phone, and he said, he told us straight away it was Milan's comet. He used the name, it was Kobayashi Berger Milan. It was awarded to 3 people, but it was mine. So that observation was made, I think, 12 days after discovery. That's the closest I've ever come to a discovery, and it was the first comet I ever saw. And that was during the summer. That comet was found on the first day of the summer break, school break. So that's on the left. But on the last day of the school break, I also found a nova in Cygnus, but I was about number 80 who saw it. So everybody remembers Nova Cygni V1500 Sig reached magnitude 2 towards the end of August. So starting off in the 1970s, these are some of my first light curves of declining novae. So it was great to get a light curve on variable stars within just a few days. Declining novae are good for that. And I've continued to do that kind of work now. So you get up to 1981, I've got a new telescope. This is early drone footage from before drones were invented, of course. And so I'm retiring the 6 centimeter refractor, and I'm replacing it with a Celestron 8. And that's when I could really double down on undertaking variable star observations. By that time, I dropped deep sky observing. My mentor, Colin Henshaw, persuaded me to take on variable stars full time. Colin's in the audience. He sat over there. Thank you, Colin. These are the telescopes which I've used throughout my observing career, based in Manchester originally. I did D16 telescopes, or Dobsonian telescopes. And what I'm currently using is a C14. I've been using that for the past 30 years. So this is where I've observed from. So two main areas. That's my original base, Manchester. I'm now in Shrewsbury. But I've observed visual. I've got visual observations in the database from all these locations within the UK. Quickly got to my 50,000 observation milestone in 1992. It was the second one after Charles Butterworth, I think, if you check the database. That was quite a milestone in those days. It was pre-cataclysmic ism observing, which Gary does. So this is when you're a red star or non-CV observer, although I observe CVs as well. And so it was a big deal. Hence the reason for the Astronomer Royal dishing out the award. All my observing milestones since then have been downhill. And I had to move from Manchester because of the light pollution there. That was the headlines in the evening news. They were putting street lights up all over where I was observing. So I had to move. So I moved to Shrewsbury. That was the view from Manchester. That's the best view you could get from the aurora. And that is a photo that's with your SLR camera or on a tripod with a cable release, 10-second exposure. That's the kind of thing you used to do in those days. And what you do now, a handheld digital camera from Shrewsbury, and you get that kind of view. So seeing conditions are so much better where I am now, and have been for the past 30 years. And that's, sorry, just go back. That's the Wrekin Hill. So that's the only light really, which is causing me an issue at the moment. UK isn't that bad, in my opinion, for observing. So I've got consecutive nights here. Earlier this year, for instance, I had 17 consecutive observable nights, and it was only broken by a business trip to Glasgow. I really didn't want to be there. So when I came back, I had 3 more clear nights. You can do photometry from here, from the UK. So if you get consecutive clear nights, you can get light curves like these. So this is SS Cygni, and that's an outburst. That's a Gibraltar type outburst, as Mark Wick called it. And one of the most difficult stars to get a light curve of is AC Her, because it varies so fast. But if you get consecutive clear nights, you can catch the minimum and get the fine detail in the light curve, all visual. I like to stretch the limit of observing from the UK as much as the sky as possible. You look at those constellations listed there, you think they're all far south constellations, but I've observed variable stars from the UK in those constellations, and those observations are in the database. I particularly like observing T-Sen and OY-SAG because, yes, they were Mark Wick's main discoveries so many years ago. So this is light curve of OY Sagittarius. Lots of gaps because it shouldn't really be observed from the UK, but it is. All these red dots here, even though it's 12th magnitude, you can pick it up from the UK. So it's worthwhile looking at that star. So I like to travel the world, though, and Jeremy mentioned that. So here, if you take but I don't like going too far away from fish and chip shops. So here is, so this is Zimbabwe. That's Colin Henshaw, by the way. If you squint, you can see him looking very posh in a tie. And he's queuing up outside Mr. Makamba's fish and chip shop in Zimbabwe. I've actually been to a fish and chip shop in Hawaii on this trip. That's Kilauea volcano in the background, by the way, with Roger Pickard and Arnie Hendon. The 3 of us were queuing up in a fish and chip shop in Kona, on the Big Island in Hawaii. These are the places around the world where I've undertaken visual photometry. Note the concentration in Australia. I've done 3 tours of Australia. That's 2 more than John Stowe and 2 less than Jimmy Anderson. If you take if you take the top 3 visual observers around the world, they're very stationary, or were stationary. They've not observed outside of their own home countries of Japan, Australia, and New Zealand. But I like to get around and see different perspectives of the world. So I like going up high here, and I go low as well. Yeah, well, only the Soviets would put oil rigs in on a holiday beach. Yeah, Tim Hames isn't here, I don't think, but that's a young Tim Hames. And so when you're going around the world, you get lots of opportunities to do other things. And this is collaboration between the variable star section and the occultation section of the BAA to observe a solar eclipse. This is Siding Spring, Australia. I've been there twice. I've taken my C8 telescope there. I've set it up alongside this dome, done a night's observing, wondering what their extra 40 inches was looking at compared to my 8-inch. That's Tenerife Observatory. On that occasion, in 2002, there was a NASA team there. They were taking images of meteors. I just done some observing, and I noted on their screen they were looking at a part of the sky which covered UU Aurigae, which is a red variable, which I just made an estimate of. I looked on the screen. It was about a magnitude brighter on there. So I informed the NASA team that they had red sensitive cameras. And they just looked at me in bewilderment, thinking, well, how does he know that? So this is another one of the visits. So this is when I went all Germanic. I drove in my BMW to observe from Kriegsmarine gun emplacement in Jersey with my Zeiss binoculars. This recess area here is where they stored all the shells for the main armament. And it was great for my clipboard binoculars and charts. Perfect for that use. So it was a lot more useful than what I used it for. Another gun emplacement, this time a British one. This is one of the guns which Colonel Warwick would have provided ordnance for on Gibraltar. It was there at the time that he was there. And it turns out the gun emplacements are actually good. They give you panoramic views. They're good places to observe the sky from. So I've done that in several places around the world. And this is typically what you do. With a C8 telescope, it's quite easy to set up within minutes. You can throw it in the boot of a car. You can drive around, go to the top, the highest point on wherever you're going. This is Antigua. Again, this is these are blockhouses which was built by the British Army way back many years ago. But it was the best viewing point from the island, so that's where I observed from. I've gone to several international meetings with all competitors, AVSO and ORSNZ. Great to meet all these people. Sad that Charles Scoville, Janet Matai, Mike Simonson from the AVSO, Frank Bateson, Albert Jones, and Brian Warner recently are no longer with us. Most emotional event for me, Germany was there. I think you may have even taken this photo. Was when I gate crashed the AVSO centenary meeting and dished out a Charles Butterworth Award to Mike Simonson. The only time he couldn't speak, and there was actually a tear in his eye. These two guys left, so Rod Stubbings and Albert Jones, they're the two leading visual observers in the world. Great to meet them, real good friends. Sadly, Albert's gone. I think in time, Rod will overtake Albert's total of over 500,000 visual observations. So, yeah, so this is a little bit of detail observing time, which I've done. So the most observing in the night I've done is from Shrewsbury. And the longest single observing session was earlier this year from South Africa. And that's the two minute figures that are given in red. Note that most of these are are either in Australia or overseas. And that's because it's more comfortable weather there, warmer conditions than Manchester or Shrewsbury. If you do get a long clear night though, you can do time series. So this is a time series of a dwarf Cepheid way back in 1981. So got 4 cycles in, and you can do that visually. There are hazards with observing around the world. And Colin, by the way, do you remember taking that photo? Colin?
Sorry?
Do you remember taking that photo 43 years ago? Well, maybe you don't. Okay. Yeah. So yeah, there's various items there which are issues. In terms of the police officers, I've had them. They've asked me to move along when I've been observing in the Canary Isles. When I was on the Channel Isles, they were particularly interested in what I was doing, so I showed them Jupiter and Saturn through the telescope, and they wouldn't leave me alone. I had to push them out of the way. I needed to get on with my observing. So there is a difference to what you find. And Sean, I'm sorry about comparing police officers to baboons and puff adders and such like. Right, let's get into some science. So the great advantage of visual observing is the longevity. I've been doing it for 50 years. So you get long baselines of data. So this is the kind of thing you can see long-term changes in individual variable stars. So here are two examples of Mira stars, which are the mean magnitude is all over the place. So got to keep observing this, and I'm going to keep on doing it as long as I possibly can. Here's one where a Mira star is reducing in range. And where is it going to go? Well, we're going to keep looking at it. That's my plan. And then suddenly you get a Mira which is pretty stable, and then it does this. And then it has a record maximum and record minimum, and then carries on. So you've got to keep observing them to understand that and detect these things. And two semi-regular binocular stars over the long term, you can see the long-term changes. Sometimes it almost shuts down. Other times the magnitudes range much greater, and it's the same on both of them. And you can see there's long-term changes. And if you take, when I started observing this star, it was classed as an irregular star, but it's clearly got a period. So it's now a semi-regular star. So that is, and there you can see it switches between periodic variation and irregular variation, and the range is changing significantly. Take Corbeau. So this is the record fade down to 15th magnitude. Took a long while to get back to normal. It actually, if you look at this curve here, it only actually got up to magnitude 6, mean magnitude 6, earlier this year. So that fade lasted from 2007 all the way through to this year. Most people have said it's been back up at maximum for a few years now. So this is a comparison of my visual data with AVSO-V data. So you can see it's aligned here. My visual data is consistently brighter here. That's simply because of the color effect. And you can see that it tracks back down level with that. And you get a small dip here. So that, and it's confirmed by the V data as well. And so that's something that requires a bit of an explanation. I think that's a merge precursor with a main outburst. Take the SS Cygni. We saw what happened a few years back in 2021, I think it was. The rain, a few people said, oh, it's going into standstill. Well, no, it was just a gradual reduction, and then a reduction in range, and then it recovered again. But it seems to have happened to a lesser extent in a few other places as well. So again, you need to keep observing these. This is the star which I've observed the most. I've observed this star every 3 nights on average for the past 43 years. You can pick up long-term trends. This is these are the standstill. That's the record standstill, and other standstills here. But you also pick up areas where it doesn't go faint for some reason. So, and again, it doesn't get very bright during this period, but on other occasions it gets brighter. So you can see you've got a record here of the energy output or visible energy output coming from the system. XPER is in the news at the moment, also there's a bit of investigation going on over it. I've done 6-month means on this one, just to show that there is maybe a cycle of about 29 years. So it's just coming out of minimum at the moment. And so that's useful for the people who are doing the research on it at the moment. They'll understand if they're cross-referencing with previous data, previous scientific works, what the star was doing at the time. If you observe a star for a long period of time, you can even actually see it transition from one type to another, and that's what's happened with AG Peg. So AG Peg was a long time declining nova. It was declining at a rate of about 0.2 of a magnitude every 10 years, which is what it's doing here. And then it switched. Yeah, I'm on schedule. Then it switched to Z-and and had this outburst here. This outburst, which confirmed the transformation to Z-and, that's what went out on a BAA VSS alert and alerted the world that this star had truly transformed. And that's the full light curve. So you can see on the left, declining nova. It shut down at this point here in October 2003, then it moved to Z-and. And these cyclic periods, that's the orbital period. Another Z-and star. Look at that beautiful light curve, long term, goes beyond where we've got V data starting in the 1970s. Very little V data in those days. But you've now got a consistent, this is using one chart, one sequence, so it's fully consistent, internally consistent. AB Auriga last night, faintest it's been recorded in 100 years. I can confirm that, and I think Sean's confirmed that as well. But for many years, it didn't do anything. I monitored it for, I think it was 17 years, and it brightened 1/10 of a magnitude. I persevered, and then we got this fade. And so look what happened to the mean magnitude. It reduced. And we got another fade, but you only got 2 fades in about 40 years. And look what it's doing now. It's up and down like a yo-yo. So it's going through a dust period, dust obscuration period, lots of activity. There's lots of science going on with that system right now. Everybody should be looking at it, but I don't see many other than visual observers looking at it. So please pick up on it. T-core bore, I have to mention T-core bore. So this is combined visual data, which is all the black dots with the A of ESO. You've got some V data, but if you plot my visual data in blue as well, you get a more complete picture to what the V data is giving you. That again is something perhaps worthwhile considering, because any scientific analysis using A of ESO data would be focusing just on this, whereas I've got a more complete picture. And look, the systematic difference between the two is simply because of the color difference between the variable star and the comparison stars. And when the star goes blue, it merges. And that's T-core bore at the moment. So I'm observing that intensely. At the moment, my rate of coverage is 47% from the UK, which is good. So I'm going to try and keep that up. And but probability of me picking up an outburst is quite remote. Final light curve is of the nearest quasar. So these are annual means. You can see the overall trend there. It's as faint as it has been in the past 40 years. So that's, I'm just waiting to pick that up now. So whilst I'm observing, I picked up these comets. Besides the one I mentioned, so I found 12 others. You observe, if you go out observing variable stars, you'll pick up comets. Same with asteroids. So I picked up all those asteroids. I even found the planet Uranus one night next to V, Aries. I wonder what's that. And that's a summary of milestones. One thing to point out is these the 100K observation milestone and 200K milestone. Those observations, the stars selected for that were done by the VSS director. So anybody who's looking to succeed Jeremy, that's one of your duties going forward. You would have to select my next milestone. And just to end up, what I'd like to say is that visual observing is real fun, because you get out there, you get to see the sky. I've seen meteors, fireballs, aurora, noctilucent cloud, zodiacal light. I've even seen the Gegenschein. although Rob McNaught had to point it out to me. The Milky Way looks beautiful. You see all kinds of things. The sky is a wonderful thing. And I would encourage you to get out there. When I get to the end of the night, like on this image here, which is from Northern Territory, Australia, I sometimes look, watch the sunrise, watch the sky lighten as the stars disappear, just sit back and enjoy it. And then on this one, yes, we've got the planet Mercury just peeping through the trees, and it's a glorious sight to see. So here's to the next 50 years. Good night.
Thanks ever so much, John. Any questions for John?
John, I owe you an apology. In my talk, I said that Gary was probably the only person who would be able to observe extragalactic variables visually. You have just recorded 16.6, which is way easily within range of some variables in the in M31.
Yeah, it's not just me. There's quite a few of us. Yeah. No problem. All right.
Richard.
Great talk, John. Very interesting. Thank you for that. I've got a silly question, but it's something that's been bugging me for 55 years that you may be able to help me put to bed. Your opening slide, where you showed as a young lad that 6 centimeter refractor.
Yeah.
I recognized it instantly because I too was presented with one of those by my parents when I was about 14 or 15. By that time, I'd already been doing astronomy for about 4 years. I got the bug very early, and I'd already had a couple of smaller refractors. So I could tell a reasonable good view, telescopic view from a bad one. And when they got me that one, I was really excited because it looks the business, doesn't it?
Mm.
But when I looked through it, the image quality was rubbish. And cut long story short, much to their disappointment, about a year or so later, I was so dissatisfied with it that I got rid of it, traded it in for a tape recorder or something. I don't know. And I've always wondered, I suspected I'd just got a bad one. For some reason it was a bad quality one. But you've obviously kept yours for a while, so you must have had
I've still got it.
You still got it?
It's just in the garage. It's stored away. It's been stored away for 40 years. It was good quality. You saw the pencil sketches of the planets.
Yeah.
Yes, I could see the belts on Jupiter and the rings of Saturn. Yeah, I could see all that.
Yeah, I certainly remember looking at that it was one of those, and I must have just, as I say, been given a bad one. But I'm glad yours is fine.
No, mine was good. Thank you.
Final question from me. So where next? Where would you like to go and observe variable stars from next? What's on the top of your hit list?
I was thinking there's a solar eclipse in Spain next year.
Yes.
I was thinking about going there, not to observe the solar eclipse, but during the course of it, maybe observe some variables close to the sun.
Yeah.
So I was thinking maybe that's the next challenge.
Yeah.
I've not decided yet whether to do that, but that's what I was thinking when I was driving down here today.
Fantastic. John, thanks so much. Very good. So our final speaker of the day is our special guest, Ingrid Pelisoli. Ingrid studied for her undergraduate and her master's and her PhD in Brazil, and she came to the University of Warwick in 2017. Then you had a postdoc in Potsdam, and you returned to Warwick in 2020. So at the moment, Ingrid is Assistant Professor and Royal Society University Research Fellow in Astronomy and Astrophysics at the University of Warwick. And you primarily work on white dwarfs and transients in the white dwarf and transient group. Her main goal is to understand how binary interaction can affect the final stages in the life of a star. So Ingrid, I think you're an excellent person to speak on discovering and characterizing white dwarf pulsars. So thank you very much, Ingrid.
So first of all, thank you very much for the invitation to be here. I really love talking to astronomy societies. It kind of reignites my love for astronomy again. So thank you very much for having me. And thank you for the introduction. I don't have to say my name again, but yeah, I'm Ingrid, and I'm here to talk to you about discovering and characterizing white dwarf pulsars. So there's two main parts to the title of my talk. We have white dwarf and we have pulsars. Usually, when people are talking about pulsars, they are talking about something like this, which is a neutron star that is spinning very fast. And as it does that, it emits a beam of radiation out of its magnetic pulse. And wherever this beam aligns with a line of sight, we detect a pulse. And that's where the name comes from. It's kind of a lighthouse effect. These systems were first detected in radio by Dame Jocelyn Bell Burnell many years ago now. And we still don't understand exactly what is going on here. But what I think is happening is that in the poles of this neutron star, which is a very, very compact object, they have sizes of only a few kilometers, up to 10 to 12 kilometers. So they are very, very compact. In the poles, there are conditions for the light particles, for the photons, to break into a pair of particle and antiparticle. And this pair of particle-antiparticle, they are charged and they get accelerated by the magnetic field. And when you have charged particles being accelerated, they emit light. So that's what we think is happening over here. The most famous example of a pulsar is the Crab pulsar that sits in the middle of the Crab Nebula, as shown in this very nice composition here. So some of you that like observing deep sky objects might have seen the Crab Nebula before. The reason why I'm talking about pulsars now is essentially to get it out of the way, because that's actually not what I'm talking about. I'm not here to talk about this type of pulsars. Because when you put white dwarf pulsars in the same expression, in the same sentence, you get something that is actually quite different from these neutron star pulsars. They are the traditional type of pulsars. And you might get a sense of why they are different just by looking at this artist impression over here. But I'm going to go into a little bit more detail than just an artist impression. So I'll go back to the first part of the title, white dwarfs. And I'll talk a little bit about what these stars are and what are their main properties. So the first thing you need to know about white dwarfs is that they are the most common stellar remnants, which means that over 95% of stars, including our sun, will one day become white dwarfs. The way this happens, and I'll go through a little bit of the physics of this, because in my opinion, stellar evolution is one of the most beautiful and most intuitive things in physics. So I think it's worth explaining to you how a white dwarf is formed. So we start with a star like our sun, and what our sun is doing at the moment is burning hydrogen into helium in its core. And that's what prevents our sun from collapsing onto itself, because the sun has the gravity pushing everything in, but this burning process in the core has energy release, so that counterbalances the gravity. But eventually, the hydrogen in the core ends. You don't have fuel forever. When this happens, there's nothing to counterbalance the gravity anymore, and then the core starts to collapse. As it does that, it releases energy that causes the outer layers of the star to puff up. And that's how you get a red giant. Our sun will do this in about 4 billion years. The sun is kind of a middle-aged star. It has now around 4.5 billion years. And when it does that, it will definitely swallow Mercury and Venus, and will probably swallow the Earth as well, just to give you an idea of the scale of that. As this core that is now of helium is contracting, at some point, it will reach the conditions in terms of temperature and pressure to start burning the helium. And when it does that, it will form carbon and oxygen, and then we reach a new stage of equilibrium. So now there's the energy of helium being burned to counterbalance gravity. So the core remains stable again. For most stars, they will never reach the conditions to burn carbon and oxygen. So we form a carbon and oxygen core, and that's the end of it. But in the meantime, the outer layers of the star are still burning helium and oxygen, helium and hydrogen. And because the star is very big, these outer layers, they are not very bound to the core anymore. So the energy release from these burning processes cause the outer layers to be spread away. So the star loses its outer layers, and the outer layers then get illuminated by this hot carbon and oxygen core that is now exposed. And that's how we get a planetary nebula. The outer layers of the star were lost and are illuminated by the hot core. With time, these outer layers fade away and get moved away from the star, exposing this carbon and oxygen core that is surrounded by the hydrogen and helium that have been left over by stellar evolution. And that's how we get a white dwarf. So the white dwarf is basically just the exposed core of a star. It has a size that is similar to the Earth, but a mass that is similar to the sun. So they are very, very compact, very compact, and they have gravities that are 10,000 times stronger than the gravity of the sun. Only the most massive stars, the ones that have masses above 10 times the mass of the sun, go through a different pathway. And that's because in these stars, because they are very massive, they do reach pressure conditions to keep burning things beyond carbon and oxygen. So just keep burning things, and that's how most elements are formed. In the beginning of the universe, we just had hydrogen, helium, and lithium. Everything else has been made by stars. So the stars keep burning things until they form iron. And then iron is a very, very weird element, because when you burn iron, instead of releasing energy, you consume energy. So instead of counterbalancing gravity, you're helping gravity. So the whole star collapses. And when it does that, you go supernovae. So the elements get scattered away. And depending on the initial mass, you leave behind either a neutron star that can be observed as a pulsar, depending on the conditions, or a black hole. So even though people love talking about black holes and neutron stars, this is the end stage of only 5% of stars. Most things will actually become white dwarfs. That's why they're my favorite type of star. Some important properties of white dwarfs are it's their rotation periods, which are actually fairly slow. And that is because when the stars lose their outer layers, that carries away a lot of energy and carries away angular momentum. So even if the star was spinning very fast, when it reaches the white dwarf stage, it's usually spinning quite slowly. So this is shown here in a histogram. This is number of stars versus rotation period for white dwarfs. And there's a peak around 30 hours. So the typical rotation period of a white dwarf is of the order of a day. So the same rotation period as the Earth. On the other hand, even though they have very slow rotation, they actually have very strong magnetic fields, which is something we don't quite understand why. We don't really know where these magnetic fields come from. It's still an open question, but they are very strong. So again, I'm showing this in terms of a histogram. The red histogram here is sensitivity. So it's observations that were done, and they are sensitive to magnetic fields of only down to around 1,000 Gauss. To give you an idea, the field of the sun is 1 Gauss. So these white dwarfs are way stronger in terms of magnetic fields. And the blue is detection. So the magnetic fields that we detect are at least 10,000 kilogauss, so 10,000 times stronger than the field of the sun. And this is just an observation of fact. And this happens for around 30% of white dwarfs. And another important thing about the rotation and magnetic fields of white dwarfs is that this can be affected by interaction with a companion. It can be affected by binarity. And we find that around a quarter of white dwarfs are in binary systems. This is not surprising because a large fraction of stars in general are in binary systems, so white dwarfs are no different. This is shown here with this pie chart, which is done from simulations, but they agree very well with the observations. And the binaries here are the red, green, and the magenta. So it's around a quarter, maybe even more. A fraction of these binaries have cool main sequence companions, M dwarfs. And a fraction of those are in a very interesting configuration where the white dwarf and the M dwarf interact. These are, of course, the cataclysmic variables, which we heard about a little bit already today. So in the cataclysmic variables, what happens is essentially the M dwarf is so close to the white dwarf that its outer layers are beyond the region where the gravitational pull of the M dwarf wins over the white dwarf. So the white dwarf starts stealing mass from the cataclysmic variable. And as this mass is transferred, it gains energy. So when it reaches the white dwarf, rather than falling straight into the white dwarf, it will form a disk because it comes with a lot of energy. And then when it falls onto the white dwarf, it can cause the white dwarf to spin out because it brings a lot. This is the normal configuration of a cataclysmic variable. But if you have a white dwarf that is very magnetic, you'll have something a little bit different. In this case, the magnetic field of the white dwarf kind of works like a barrier around the star, just like the magnetic field of the Earth is a barrier against the solar wind. The same thing happens on the white dwarf. And then the matter, rather than forming a complete disk, will form just an interrupted disk or an intermediate disk. And these systems are known as intermediate polars. And normally what we see is that the white dwarf in there is spinning very fast. It's spinning faster than the orbit, probably because it was spun up by this accretion of matter. If the magnetic field is even stronger, if it is at least 10 million Gauss, then what we see is that the disk doesn't even form because the magnetic field completely erases this disk. And the matter is only accreted along the magnetic field lines. And these systems are called polars. And what we see as well is that the rotation of the white dwarf is synchronized with the orbit. And that's probably because the magnetic field is so strong that it causes the white dwarf to break and synchronize with the orbit. Observationally, we know nowadays over 1 million white dwarfs. That's thanks to the Gaia satellite that has helped us find all of those. These are the ones plotted over here. This is just an observational HR diagram. So this is absolute magnitude versus color. And these white dwarf candidates are colored by what we think is the probability that they are actually white. So we have at least 350,000 that are high white dwarf probability. So that's a lot of white dwarfs. And we have about a few thousand CVs, or a few thousand confirmed CVs, which are the red ones over here. So CVs, or cataclysmic variables, like I said before, they have both a white dwarf and an M dwarf. And for Gaia, they are not resolved. So Gaia sees them as just one star. So you combine the blue of the white dwarf with the red of the M dwarf, and they usually end up somewhere in the middle. Some of them have brighter companions that are more evolved, so that's why they end up over here. But most of them sit somewhere in the middle. And even though we have almost 1 million white dwarfs, thousands of CVs, until very recently, we had only one white dwarf pulsar, which tells you how special this kind of star is. This one white dwarf pulsar is a system called AR-Scorpii, or AR-SCO for short. And I'll talk you through the discovery and characterization of the system, which I think is very interesting. So AR-SCO has an average visual magnitude of 15. You might think this is faint. For a white dwarf, this is very, very bright. And this is the brightest star I'm talking about today. I think there might be a few that turned out not to be so interesting that are brighter, but this is one of the brightest ones I'll talk about. And because for a white dwarf it is quite bright, it has actually been known for many years as a variable star. You can see a light curve over here. This is not its original light curve, but it probably how it looked like when it was first observed in the 1970s, I think. This is a light curve from a survey called Catalina. And you can see that it shows a 3.56 hour period, and it has this asymmetric sawtooth shaped light curve. I'm sure so many of you observe variable stars, right? If you saw a light curve like this, would anyone try to classify it and say what kind of variable star this is? Would anyone take a guess? No? That's fine. So in the 1970s, this was classified as a delta Scuti variable. It's not the first time delta Scutis are mentioned here. And this would definitely have fooled me as well. Delta Scutis, they have periods of this order, and they have light curves that look quite asymmetric. But if you look closely enough at this light curve, you will notice something weird, which is that there is a lot of scatter when the star is at its brightest, when it should be easier to measure. It shouldn't be as a scatter when the star is at its brightest. And that's because there's something very, very special happening in this star, which was actually noticed by amateur astronomers. So please keep observing the stars, even if they already have a classification, because sometimes professional astronomers get it wrong, which was the case for this star. So these amateur astronomers, when they noticed there was something very special about the star, they got in touch with astrophysicists at Warwick and told them something is happening, go and have a look. And we were very glad they did, because then we pointed the biggest telescope with the best camera we could put our hands on to see what was going on. So the light curve you saw before, the exposure time was 30 seconds. The exposure time here is 0.1 second. This is taken with a hypercan instrument, which is probably the best camera you can have. It sits now on a 10-meter telescope. Back then, I think it was only a 4-meter, but that's still very, very big glass. And what you can see here are 5 light curves, which are taken simultaneously with hypercam. It goes all the way from the U band to the Z band, so near UV to near infrared. And what you can see is pulses. So that's what was causing that additional scatter. And when you observe it faster, you can clearly see that they come in terms of pulses. And that happens at all filters that we observe, all the way from the U band to the Z band. So people wondered, well, does it do this in other wavelengths as well? And the answer is yes. So it was observed also with HST. So this is proper UV, not just near UV. This is a ultracam, which is another optical instrument. This is near infrared, and at the bottom is radio. Later, it was observed in X-rays, and it does the same thing in X-rays. On the right over here, you can see a zoom in around the pulses. They are very clear in UV, optical, and near infrared. They are not so clear in radio, but trust me, they are there. You can see the ups and downs. So this is looking very interesting. It's something that is pulsing at all wavelengths, but what is the periodicity that we are seeing there? So we can take one of our optical light curves, do a Fourier transform, which is simply take the light curve, which is in time domain, and change it to the frequency domain, whereas where a peak will tell us there is a period there, right? This is just what is happening. And if you do that, you see lots and lots of peaks coming from a Ayer's-Coe light curve. But actually, all of those can be traced to only two different periodicities. One is the originally observed 3.56-hour period, and the other one is 1.95 minutes, which is quite fast. And this was very intriguing back then because there was something pulsing every 1.95 minutes in radio, and there was nothing known that could do that. The only thing that we know to pulse in radio are the pulsars that I mentioned before, but they have periods that are much, much shorter. They are much shorter than 1 minute. They are sometimes milliseconds, and even the slowest ones we know are only a few seconds. So this couldn't be a neutron star pulsar. It had to be something else. To solve that puzzle, people went and took a spectrum of this source, and it looks like this. It might look familiar now because it's similar to what David showed us before, right? So we see the titanium absorption bands over here. We see similar emission lines like the ones we had before. But the interesting thing here is you can clearly see that even though we have an increase of flux towards the red, there's also an increase of flux towards the blue. Stars cannot be blue and red at the same time. This is actually two stars. We can clearly see a contribution from a blue star and a contribution from a red star. And we can add up these contributions to see what's going on. So now the blue star is down here. The red star is in green. I don't know why the red star is in green. Don't ask me. I find that very counterintuitive. But anyway, the red star is in green. And we can add these two and subtract from the black one, which was the spectrum that we observed. And it explains most of the features. But it does leave behind something. There is this magenta line over here that can't be really explained by the stellar components. And this magenta line has in itself two components. There is this continuum emission that is rising here towards the blue, and there are some very, very narrow emission lines. I'll be coming back to those later. I just wanted to emphasize not everything is coming from the two stars. There's some additional light in the system that is probably causing the pulses that we are seeing. When we have two stars in the same spectrum, it can be because of two reasons. One, they are simply aligned in the sky and not connected at all. And the other one is that they are actually a physical binary. The way to determine that is to do radio velocities and check if the two stars are moving around the common center of mass. If they are, we are going to see those bright emission lines as well as the absorption lines moving back and forth due to the Doppler effect, and we can use that to measure velocities. And here's a plot that is, again, very similar to a plot that we have seen before, which is great. So I don't have to explain a lot what is here, but this is basically the vertical axis is time, and each horizontal line here is one spectrum, and the yellow are the bright emission. And here is the zoom in on the H alpha line, and you can clearly see that the line is going back and forth. So this is a physical binary. And in fact, if we measure the period of the radio velocities, we find that the period is 3.56 hours. So that originally observed variability is the orbital modulation in the star, which leaves the 1.95 minute period to be explained. That one is a little bit tricky, but we do have a white dwarf in the system. And because white dwarfs are very compact, they can spin fast without breaking apart. So we infer that the 1.95 minute has to be the rotation of the white dwarf. The M dwarf could not spin that fast without breaking apart. So it cannot be the M. Definitely the white dwarf that is rotating that fast. So with these ingredients, a rapidly rotating white dwarf in a binary with an M dwarf, we can come up with a model for that emission that we are seeing. So what we think is happening in the system is we have this white dwarf in the middle, which is rapidly spinning. And then we have an M dwarf. The M dwarf is probably tidally locked, so its rotation period is the same as the orbital period is tidally locked, just like the moon is tidally locked to the Earth. Both of these stars are probably magnetic. M dwarfs are usually magnetic anyway, and like I mentioned before, white dwarfs are at least 30% of the cases magnetic. The magnetic field lines of the white dwarf are represented by the spiral over here, and the ones of the M dwarf are these two lobes. And there's a region in between the two stars where the magnetic fields kind of connect with each other. When this happens, there's a phenomenon called magnetic reconnection. Essentially, it just means the magnetic fields kind of aligned. And when you have these conditions, you can convert magnetic energy into thermal energy, and then you heat up the face of the M dwarf that is facing this region. When you do that, you can ionize material and free up electrons. These electrons are then accelerated by the magnetic field and emit light at all wavelengths. So the last step in all of this is the same as the neutron star pulsars. You have electrons being accelerated in a magnetic field, but where these electrons is coming from is completely different. And we think the face of the M dwarf is being heated up because those very bright emission lines that we see are consistent with an irradiated star, just emission lines from the very heated up face of the M dwarf. If this doesn't look interesting enough, I also have an artist's impression that might be a little bit more interesting. What we think is going on again is just this fast spinning white dwarf. You can see its magnetic field, and whenever the magnetic field aligns, we get a pulse. These beams coming out of the white dwarf are a little bit of an exaggeration. I would probably have asked the artist to remove them because we don't think the beams are always there. It's just when the magnetic fields align that we have the beam radiation. But it gives you an idea of what the system might look like. So I said the white dwarf is rotating with a period of 1.95 minutes, but I also told you at the beginning that white dwarfs typically rotate with periods of a day. So this is a very fast white dwarf. How can it be spinning so fast? I also mentioned that there is a way to make white dwarfs spin faster, which is by accreting matter. If we take intermediate polars that I mentioned at the beginning that accreted in the cataclysmic variable phase, they do rotate very fast. The fastest one has a rotation period of around 25 seconds, all the way from here. There's quite a few with periods of a few minutes, and then there's this peak on 10 minutes. But in ARSCO, the white dwarf doesn't seem to be accreting at all. And the way we can tell that is because these emission lines, they are very, very narrow. If the white dwarf were to be accreting, there will be matter being transferred from the M dwarf. And as it travels very fast. And when you have matter traveling very fast, you broaden the emission lines. And we see no signs of these emission lines being broadened. We also don't see any sign of flickering in the light curve like you get from cataclysmic variables. So we are very sure there is no accretion of matter in this white dwarf. And that's probably because the magnetic field is actually working as kind of a barrier. So the white dwarf can't accrete enough mass to spin up. And that brings us a problem. How can this white dwarf be spinning so fast if it cannot accrete enough mass because of its magnetic field? And the solution to this problem was proposed only 5 years ago, so it's very recent. And the solution is very elegant, and it says that ARSCO was probably actually not born magnetic. So what this proposed model says is that ARSCO started just like a normal white dwarf, slowly rotating in a binary that is not even accreting mass. And we see many, many of the systems out there. So they do exist. So they think that's how ARSCO started. With time, the binary is losing orbital energy. The M dwarf is getting closer and closer to the white dwarf. At some point, they start transferring mass, and the white dwarf can then be spun up by accretion. Again, this is another type of system that we do observe. This would be a normal cataclysmic variable. With time, the white dwarf, what it's doing is what all white dwarfs do, which is just cool down. And as white dwarfs cool down, we observe that they are more likely to be magnetic the cooler they are. We think this might have something to do with a phenomenon that happens in the core of the white dwarf, which is crystallization. So if you cool down water, it turns into a crystal. If you cool down the core of a white dwarf, it also turns into a crystal. And because the core is a mixture of two elements, when it turns into a crystal, the elements kind of separate from each other. And this simulates a convection zone. So you have moving charged particles. And when you have moving charged particles, you have a dynamo and you generate a magnetic field. So as the white dwarf cools down, it generates a magnetic field. And what happens here is that the magnetic field will disrupt the inner disk, and we will observe this as an intermediate polar. So a fast spinning white dwarf with a little bit of a magnetic field. With time, the magnetic field is getting stronger and stronger because of this dynamo. It connects with the magnetic field of the companion, and when it does that, it transfers energy from the spin of the white dwarf to the orbit, and then the two stars disconnect because the orbit enlarges, gains energy. So we would observe a very fast spinning white dwarf with a strong magnetic field that is not accreting from its companion. And that's exactly what we see in AirScope. So this system will be observed as an AirScope. And with time, what happens is the white dwarf would synchronize with the orbit. And we actually do see that the period of the AirScope is getting longer and longer. It is spinning down, so it's consistent with this. When the star synchronizes with the orbit, we have a white dwarf synchronized with the orbit, but not accreting mass just yet. This is another kind of system that is observed. They are called prepolars. And then finally, because there's no energy being fed into the orbit, the M dwarf can again get closer to the white dwarf, and the system starts transferring mass again. But now the white dwarf is strongly magnetic and synchronized with the orbit, so this looks like a polar. So all of the different types of cataclysmic variables that I mentioned before are connected by this evolutionary model that also explains the existence of AirScope. So what it proposes is that AirScope is simply a short-lived evolutionary stage in the life of a cataclysmic variable. But we have thousands of cataclysmic variables in just one AirScope. So this phase would have to be way too short-lived for this to work out. And we know how long it would take for AirScope to spin down. So we know it is not that short-lived. So we are probably missing some system. For this to be a stage in the life of a cataclysmic variable, we need more AirScopes. Where are they? That's the question I asked myself. So I went and did a targeted search for more white dwarf pulsars. And the way I did this was simply asking myself, what makes AirScope stand out from other types of stars, and then try to find other stars that stand out in the same way. The first thing that makes AirScope stand out is simply where it sits in the HR diagram. We have lots of stars in the main sequence. We have lots of stars in the white dwarf cooling sequence. We don't have a lot of stars sitting here in the middle. So I can simply start by selecting stars that are sitting in the middle. The next weird thing about AirScope is that it varies a lot in infrared. So these are two infrared light curves from a satellite called WISE. So this is WISE-1 and WISE-2. And you can see it varies by like 2 magnitudes in infrared. White dwarfs are typically very faint in infrared, so they are not even detected. So this is very unique to AirScope. And we can find all of the stars in this region that vary in infrared. They are the red triangles. And then finally, AirScope, because it's not just the sum of star 1 and star 2, it's star 1, star 2, plus some additional light, the magenta line that I showed before, it has a weird color. So if we do W1, so WISE-1 minus WISE-2, most systems that sit in between white dwarf and main sequence are here in the middle. AirScope sits all the way over here. So we can select stars that are in this region. They are the black dots over here. And if we combine all of this criteria, we end up with 56 stars plus AirScope itself. So at the very least, I recovered the one system I'm trying to find more of. And 56 is a great number because if I write a telescope proposal saying, I want to observe 1,000 systems, they are going to say no. If I say I want to observe 56, they're going to say, yeah, that's fair enough. You can do that. So that's what I did. And I followed up these 56 candidates, both by thinking spectra and light curves. I got some help from amateur astronomers for this light curve. So the final paper, I have, I think, one amateur astronomer that was my co-author. So that's another way you can help us. And one of the stars that we observed was J1912 minus 4410, which turned out to be the second white dwarf pulsar. It's about 2 magnitudes fainter than AirScope, so it starts getting very, very faint, and is twice as far away. And it's also quite south, so definitely not observable from here. We observed J1912 with an instrument in Chile called UltraChem, and this is the light curve that we got. So UltraChem observed in 3 filters simultaneously. This is R, G, and U. This is only half an hour of observations because the instrument broke. which was very unfortunate. We fixed it for the next night, but on the first night, this is all we could get. But it was enough to see that it's definitely pulsing. And if we take this light curve and transform it to the frequency space, there is a peak at around 5-minute period. So things were starting to get very interesting. I luckily had a friend that had access to a spectrograph, so I went and asked them if I could take a spectrum, and this is the spectrum that I obtained. So again, looks very similar to AR score. We have contribution from a red star over here, contribution from a blue star over here. The gray and black is just 2 different spectra with 2 different instruments. And we also have the very narrow emission. So everything is looking quite promising. So I went and asked everyone I know if they had access to radio or X-rays, and I got a few friends to observe it in radio and X-rays, and it turns out that it's actually pulsing in all wavelengths, just like AR score. So this is light curves on the left. On the top is radio, then is the 3 ultracam bands from the near infrared to the near ultraviolet, and in the bottom is a light curve taken with a satellite called XMM Newton that does X-ray measurements. In the middle, you can see the pulses in all wavelengths, and on the right is the frequency space where we see a few different peaks. But again, all of the peaks that we see can be explained by just 2 different frequencies. One is 4 hours, and the other one is 5.3 minutes. And if we go and do the radial velocities, we see that the 4 hours are the orbital period of this binary. These are the radial velocities, and here is the light curve that looks very similar to the light curve. So we can say that 4 hours is the orbital period, which leaves the 5-minute period to be the rotation of the white dwarf. So with this, great, we confirmed that J1912 is another white dwarf pulsar, but out of all of those 56 systems, it was the only one, which was disappointing, but not extremely. At least we found one. So the 56 systems here I plotted with different colors. The green circles turned out to be polars. The inverted orange triangles were just normal CVs. The 2 magenta squares are intermediate polars. This one was looking very promising at the beginning, but then turned out to be just an intermediate polar. The crosses, black crosses, are systems that vary in infrared, but didn't vary at all in the optical. So either they only vary in infrared, or the variability in infrared was contamination because of a background source. So I didn't bother with them. And the red triangles here are young stellar objects that we were talking about before. Yes. So young stellar objects, they are very variable in infrared. So my selection for infrared variability ended up being what caused all of this contamination from my perspective with young stellar objects. But at least I found one white dwarf pulsar. So I put a lot of work into finding this one white dwarf pulsar. And in the meantime, I had some colleagues just looking at spectra from a survey called Sloan-Gestel Sky Survey, which uses this very funky looking 2.5 meter here to take spectra of millions of sources. And one of my colleagues, Boris Gensike, who some of you know, emailed me saying, oh, I found another white dwarf pulsar just by chance. I'm like, you didn't. I've been doing this for years. Come on. And then he was actually right. This system was called J2306. Its magnitude is 20. So now we are getting really, really faint. You probably cannot do this by eye, John, whatever you are. If you can, that would be very interesting. This is the spectrum that Boris, my colleague, sent me. So yeah, I can kind of see it. You do have an increase to the red. You kind of have an increase to the blue, and you have very narrow emission lines. But at this stage, I was very, very worried about young stellar objects. And they kind of look like this as well, right? Yeah, confirmation. They do look like this. They don't have this increase to the blue, but they also have this very narrow emission lines. They also have the titanium band. So I said, okay, not convinced. Let's get a light curve and see if we can find the pulsars that we expect for a white dwarf pulsar. And this is the light curve that we got. It's a Mag 20 object, so it's very hard to observe. And its location in the sky means that we couldn't use ultracam, which is our go-to instrument, we had to go to another instrument that sits in Thailand called UltraSpec, which despite the name does light curves rather than spectra. It's only on a 2.5 meter telescope, which is very small for me. Might sound big for you, it's very small for me. So in this light curve, we can definitely see some modulation. This is a 3.54-hour light curve, so there's probably some orbital modulation here, but I can't see any pulses here. Can you guys see any pulses here? Probably not. But that's where the power of doing a Fourier transform and putting things into frequency space comes, because if we do the Fourier transform of this, there is a very, very clear peak at 1.54 minute period. So don't always trust your eyes. If you have the ability to do a Fourier transform, please do, because you might find more variability than you were expecting, which was definitely the case here. So we continued to follow up this object, and we found out that just like AirSCO, it has many peaks in its light curve, but all of this can be traced to only just two frequencies. One is 3.49 hours, and the other one is 1.54 minutes. So again, we have the rotation period, which we can confirm with radio velocities, which is this 3.49 hour, and the 1.5 minute period is the rotation of the white dwarf. We don't have the pulses in all of the wavelengths yet, because this is a very faint system and it's very hard to observe. But with what we have so far, we are very, very convinced this is a white dwarf pulsar that was found completely by chance. After all of my efforts in trying to find them, someone found the matches. But at least they told me about it and let me be part of the discovery, which was and even though I was looking at all of this parameter space over here, and my colleague was just looking at cataclysmic variables, so it was also all over here, the two new white dwarf pulsars sit right next to AirSCO over here in this parameter space, which is very intriguing. We don't know why this is yet, but it's definitely something that we'll be exploring in the future. So just to conclude, so if you learn one thing today, let it be that white dwarf pulsars are a very rare class of radio emitting stars. Their emission is powered by binary interaction, not like the neutron star pulsars that can have pulses even when they are in isolation. That's because the white dwarf cannot generate electrons by itself. It needs them to be fed by the companion. The existence of these pulsars can be explained as a short-lived phase in the life of a cataclysmic variable. And we now have at least three sources. So this is starting to be consistent with this short-lived phase. But to be completely sure of this, we definitely need more of the systems. So the next steps in this is, first, we want to further characterize the systems that we already know. For example, try to confirm that the third pulsar, J2306, has a radio emission. We have some preliminary data that says yes, but we are not convinced about the pulses yet. And the other thing is find more. And what I'll probably do is just search here. I don't have to search everywhere. Apparently, they are all here. So that's what I'll do. If I find any bright ones, I might get in touch with some of you guys to follow them up. And we'll probably use radio as well to find them, because if they are pulsing in radio with minute periods, they are probably easy to find, because not many things in radio pulse with minute periods. So we'll probably use arrays like LOFA and MWA, which have this funny looking shapes. They are not the kind of telescope I'm used to, and probably not the kind of telescope you're used to, but they are very useful despite it. And I mean, that's it. Thank you very much, and I'll take any questions that you might have.
Thank you very much, Ingrid. So questions. Oh, David's got his hand up already.
Have you noticed any changes in the spin period? Which direction are they going?
So AirSCO is getting slower. So the spin period is, the period is increasing. And for J1912, we think it's also doing the same. It's preliminary data because we don't have a very long baseline, but it seems to be doing the same. So the spin is slowing down, and it will eventually probably synchronize with the orbit, as the model suggests.
How many CVs are likely to end up in this state?
That's something I've been asking the theorists. If the model is correct, it will be a fraction of them, not all of them, because they have to have the magnetic field to emerge just at the right stage. So the numbers we don't know just yet. They told me we should have a few tens in the galaxy. So 3 still not enough, but we are getting there.
Thank you.
Any other? Yes. Yeah, just wondered, in your new circle of search, your little circle, have you any idea how many candidates you might have to ask for the telescopes to study?
Probably a few hundred.
Okay.
Yeah, depends on where I do my cuts, but probably a few hundred. Yeah.
So more than the 50 that you.
Yes, because now I'm not getting rid of the ones that don't vary in infrared. Yeah.
Any other questions? So you talked about getting your application in for the 56, which was a reasonable one. So now you've got a number of different instruments that you might want to use. How are you going to go about getting time on those, or what is the process that you'll go through?
So usually what we do is first we divide the sample by north and south.
Yeah.
So the north ones go to north telescopes, the south ones go to south telescopes, and then we divide it by brightness.
Okay.
So the brightest ones will go to you guys.
Yep.
The faintest ones will go to the biggest telescope we could put our hands on. So that,
Okay.
that will probably be the plan.
So hopefully there'll be some bright ones in the Northern Hemisphere, because we've got quite a few people keen to follow up. Look at Paul, he's chomping at the bit. Yeah, yes.
Yes, that's true.
Ingrid, thank you ever so much for coming this afternoon and for
You're
sharing your wisdom with us. It's been really great. Thank you very much. So, I'm afraid we're drawing to a close now. One point I want to make is that I know a number of people have approached Chris Lloyd for the slides that have the various links that were shown towards the end of his presentation. He's going to send me a PDF of those. So if anybody would like to see those, please email me and I'll whiz them across to you. So thanks for doing that, Chris. So yeah, it's time to wrap up, and it's time for thank yous. The first thank you needs to go to our friends here at the Northamptonshire Natural History Society. I don't know whether they're all out there at the moment, but thank you ever so much. Thank you, Nick, for facilitating this many months ago. Thank you, Julia, for hosting us, and thank you, team, for the splendid spread you put on today. It's been absolutely wonderful. Really enjoyed it. So let's give them a round of applause. Unfortunately, it might mean that other BAA groups will be back here in the future. So just be prepared for that. Some other thank you. So Andy, thank you for jumping up and down so many times today for sorting out the IT. It's really great to have you on hand, and especially with different systems. So we'll see how the recordings come out, and if they're looking good, we'll post them and make them available to people. On wrap-ups as well, in terms of being able to sort of re-enjoy or re-engage with this meeting later. So looking forward to Tony. Thank you for making notes today. He's been busily beavering away writing, so we look forward to seeing that at some point in a future variable star section circular. Big thank you to the speakers today. I think it's been a really splendid day. In putting the program together, I was really keen that we had a broad spectrum of covering all the different aspects of amateur variable star observing, visual, CCD, digital, other forms of digital spectroscopy, and I think we've seen that today. So thank you to all the speakers, and thank you, Ingrid, once again for coming all the way from Warwick. So round of applause to the speakers. And the final thanks are to everybody gathered here. So the audience, thank you for coming today. I hope you've enjoyed today. I hope you'll go away enthused and refreshed and ready to go out and observe the variable stars. So all that remains for me to do is to wish you a very safe journey home. Goodbye, everybody. Oh, right. So any of the speakers, if they would like me to make the slides available, please send them to me with permission to do so. Thank you. Oh yeah. Okay.
Well, I know I don't. But yeah, I'd just like to add a thank you to Jeremy for organising this and making this happen.